this is the link. We also have a project template. So if folks want to see an example of how they can integrate RAJA and Umpire into the project, there's a template. There's various proxy apps that all use RAJA. These have all been used for vendor collaboration. And then there's the RAJA Performance Suite. So the RAJA Performance Suite collects a variety of kernels from applications, different benchmarks, and we use it to assess compiler and RAJA performance. So for a given kernel, we'll write it in RAJA, and we'll write it in native backends such as CUDA, OpenMP, SYCL, and we'll see how the performance varies between the RAJA and native implementation. So this lets us assess how the compiler is optimizing through RAJA. It's been very useful, just keeping track of performance. Likewise, Umpire also maintains user documentation tutorials. So there's the user guide, the link's right there, and there's an interactive tutorial that uses Jupyter notebooks. And lastly, there's what we call CARE. So this is a collection of Chai and Raja extensions, and this is a repository that builds on Raja and Chai to offer common algorithms or computing patterns and encapsulates them all in one place so different code teams can use them. Now we're going to get started with the tutorial.
So essentially where I am, if you have an instance and you followed, so I guess I can show you guys, but if you have the instance like set up, you should see this navigation pane on the side, and you can go into the intro tutorial. You can see there's these lessons, and we're going to start at lesson 3. It's very basic, but yeah, I think we're going to start at lesson 3 here. And so essentially what this is going to cover, let me go here in the chat just to kind of have this up here. And of course, this is your other thing, but okay, so we're going to start lesson 3. I like to have the markdown kind of show up. If you're in the instance and you look at the README, it doesn't really show up super pretty. So from the browser, I can look at this. We are going to start at lesson 3. It's very, lessons 1 and 2 just kind of show you how to bring in BLT and CMake as dependencies. But we have found in the past that people kind of can catch on to that, and we have already provided you with that for the start of this lesson. So we're just going to jump into lesson 3, and this one is all about bringing in Umpire. So if you remember from what Arturo was saying, Umpire is the memory management component of the RAJA portability suite. So, and in this particular lesson, you should see some to-do comments. So I'm switching back over to this, to what you would find with your instance, but you'll see these, to-dos, right? And so what you're going to have to do is create an Umpire allocator with a host memory resource, and you can allocate an array. I'll go back here so it's all pretty. So yeah, you're going to be creating an Umpire allocator with the resource manager, and everything that you do in Umpire it's always going to start by you creating your instance of the resource manager. And then with the resource manager, you can create, you can make allocators, you can get allocators. In this particular case, we want to get the host memory resource. Umpire provides you with a couple of memory resources. Host is one, and then there's some other ones like device or pinned memory, unified memory. But for right now, we're just going to start with the host. And as you might imagine, this will give you CPU memory. So behind the scenes, it's actually calling malloc, but um, we're going to do this all through Umpire. And then once you have created your allocator, you can, well, allocate and deallocate some memory. We have links to our documentation in the repo. But then what you're really going to want to do is just allocate some memory in bytes. So for this example that we have, we're going to want to make sure that we have enough for data, which is a double star. So yeah, and then you can deallocate the memory afterwards because we are good programmers. And there's more links to documentation you might find useful. But essentially, once you've made your changes, you can run make and then run this executable, and you should find that it gives you an output. So the way that this tutorial is going to work, we kind of set you up with a lesson, and then we're going to give you 5, 6, 7 minutes to go ahead and fill stuff in. If you have questions while you're doing some of that, feel free to pop that in the chat, or you can raise your hand and Arturo or myself will unmute you. Because that's another thing about these webinars that we discovered is that the automatic setting is to be muted. So I see that so while so at this point we are just going to go through and try to start trying to fill in some of the lesson. And while you're doing that, I'm going to try and answer some questions from the chat. And I see that there is someone who can't find their instance. Did you email or did you fill in the Google form? And if not, just send me a private chat with your email address and I can email you the instance.
Chrissy, there's a note here that the first link on the README gives an error.
Okay, let's try it. See this one. Okay, well, that is good to know. Oh no, I lost my link there. Okay. Okay, so this is an issue that essentially the umpire documentation, the Doxygen broke at one point, and we have not gotten around to fixing it. So that would be a link to our Doxygen, but as you can see, there is nothing there. They are created, but the link to actually post them on this Read the Docs website doesn't work. But essentially, you can go into the features, and there's stuff about the different allocators. And even, some of the tutorial on allocators here. So I can actually just post this in the chat instead, which will be much more helpful than just a broken Doxygen link. So if you have access to the LLNL LC machines, yes. Sorry, I realized that is a question that only I can see. But yeah, if you have access to the LC machines, you can just as easily clone this repo and go through the lessons that way. We have instructions on how to build or the topmost README, like how to build this. And these are LC machine specific instructions. If you are getting fatal error that it can't find the RAJA header file, so that shouldn't be the case, because in our CMake, we are depending on RAJA, so that you shouldn't be getting that if this is filled in. Yeah, maybe that is a good point, Chris. So if you are doing this from an LC machine, you will have to run a git submodule update, and we do -- init and -- recursive. So something like that. Yeah. Okay. But essentially, if you fill this in, or even if you get stuck on something, the spoiler alert is that there is a folder with the solution, which after we give you guys, if all of this was working as it should have been, and we didn't have any errors with the instances, we would give you guys the 5 minutes to go and work on this, and then we would come back and show you guys this wonderful solution here. But it is also a way that you can kind of keep up with this if things aren't working exactly right, or you get stuck on something. Just know that there is the solution, and so we grab our resource manager like you would in any Umpire program. You always need to grab your instance And then once you have the resource manager, you can get the host resource. This will give you CPU memory. And then we are creating a void pointer and allocating some memory and bytes. Um, and then we're just printing out what that data is. And then, of course, deallocating it because we are good programmers and we deallocate our memory. Yeah. Okay. So we're keeping an eye on chat. But I will keep us moving. I don't want to fall too far behind. But yeah, okay. So so I'm not like running anything. Yeah.
Christine, there's some questions here, and I think it'd be good to address them. So, Alfredo, Landon, they ran the example. They see address of data equals 0. The question is, should the memory be printed instead? So, yes, after you do the exercise. So, if you look at the exercise, there's a to-do space. This is where you allocate the instance, and then you make the allocation, and then you should print out the pointer. Does that help, Landon? I was referring to the solution. Oh, it does. It should be memory, it should not be data. Yes, you found it, Landon.
Yes, you get 20 brownie points. Or what do they say? 5 points have been added to Gryffindor. Yeah, so there are a few golden nuggets that of typos. And let us know because it is harder for us to test the solution with the way that we have things set up in the CMake files. We don't always build the solutions, and so when we update one particular thing, it doesn't always transfer over. So yeah, let us know if there is something like that, and we will make a note of it and then go back in later and fix it. Okay. Cool. So I'm gonna jump into lesson 4 because we need to get moving here. Okay. So this particular lesson is all about the RAJA for all statement. Um, so RAJA for all is your it's one of the more basic RAJA statements, and it is essentially how you parallelize a for loop with RAJA, and this is specifically for single level for loops. But so the for all is a loop execution method. It's a template, and it's going to take what we call an execution policy. And so this is kind of our boilerplate, what this for all is going to look like. So you have an execution policy there, and then you're going to send it something that we like to call an iteration space. And then the most important thing is this lambda. Um, the lambda expression is representing the loop body or the kernel body. Um, and then um, the iteration space, there's an example of that here. And in this particular example, it is an integer, of an integer type, and it's from 0 to n. So this should make a lot of sense with your for loops. You have some kind of iterator. It goes from 0 to some n, and then, so that should kind of mesh with what we know of the for loop. And then the lambda expression is going to take one argument, so that is the loop index. So our the same iteration or index that you would have for the for loop. And then what you pass in with the lambda is the loop body. So typically, whether you have a C++ style for loop or a RAJA for all, the body of the loop will remain unchanged. It is just that you have to send it the right iteration space, and you have to get this execution policy set up. But the loop body should remain the same. And for now, we are just going to start with one of the more basic execution policies. That is the Raja seek underscore exec. So this is just going to execute on the CPU. And then, as we go through some of these lessons, we will get into running the code on the GPU. But again, you're going to see this pattern of having some to-do comments and some instructions for putting in some code yourself. And then once you have put in those changes, you can compile and run and see what happens. So yeah, so go ahead. I think we'll give another 5 minutes or so, and Arturo and I will try to keep on the chat here and make sure that things are going hopefully smoothly. So if you are getting an error with the Raja header file, so you're on the instance and it says that. Um, so so on the instance that shouldn't happen. If there is a way in the terminal, so if you're in the instance setting, you can go to, file and, or no, to terminal and, get into a terminal setting. But if you can run that, so this should have already been taken care of, and it seems like it has been for some people. Um, but you should just be able to run this git submodule update command. Oh, sorry, did not send that right. Okay, there we go. And that should fix it, but yeah, for these lessons, if you go into the CMake, you should see that Raja is a dependency there. And so it should be taking care of that. So that confuses me. So it must be that the submodule, well, we can help you get through that if you're still having problems there. But to Alfredo, so the string host is a relevant term. That's within Umpire, it's essentially the name of a pre-supplied memory allocator for the CPU. So yeah, Umpire supplies a couple of different memory allocators, and yeah, so if you're running stuff on the CPU, you will have host. If you're running on the GPU, there's also device. It's, in all caps, just like host is. And that would be for, your GPU memory, which, behind the scenes would be something like a CUDA malloc or a HIP malloc. And then there's pinned, and of course that would, under the hood, call the corresponding, it's like CUDA malloc host or something like that. And then we also have a UM for unified memory. And in some of the later lessons, we'll see us using other memory resources, but besides just the host. Okay, so you can ask for a specific device number. It is an example. Well, that's probably not exactly it. But yeah, there is an Umpire example in the Umpire repo where we do exactly that. I can find that and give that link to you later. But I want to go through and just get through this solution for the Raja for all. So hopefully there's no errors in this one. We've been running some of these and haven't seen anything, but who knows? We miss stuff. So, but again, we are this is just like we had before. We have the resource manager from Umpire. We use the resource manager to get the host memory resource. We do our allocation just like before, but now we have to write in this Raja for all. So we had the structure that you saw in the README. So Raja for all. We give it the sequential execution policy. And then we have a range segment where these are just integers that we are indexing through from 0 to some n, which we have created up on line 10. And then we give it the iterator I, and then the loop body is, just assigning every element of data the value of I. And then when we see out this data later on, we can see that you should see, data at 50 is equal to 50. And then we deallocate. Okay. Yeah, you will have to create some, and as long as it is higher than 50, this should work out. But we can add that as well. So then from here, we are going to switch over so that Arturo can.
Thanks, Christine. Also, Mohammed's having some trouble. Do you think he can maybe answer some questions there?
Yeah. If you continue to have an issue, I can potentially see if a different instance would work. I don't know why it would be different, but maybe you'll have better luck.
Okay. So lesson 5. So in lesson 5, we're going to talk about the reduce operator that Raja provides. So the reduce sum is basically a operation that takes a vector or a collection of vectors, and then it takes a vector, and then it can reduce it down to a single value. An example of this is, like, for example, the dot product, or it just takes a number of values that are distributed among threads, and it just reduces it to one value. That's better yet said. So in this particular example, we'll use the sum operator. So this is under the Raja namespace. There are other types of reductions that you could do that Raja provides. For example, you can find the minimum or the maximum. For more information, we have a reducer section in the Raja Read the Docs. It has all the different operations that we support. There's an example here. So in the example that we're going to be exploring, what we have here is the calculation of a dot product. So in this exercise, what we're asking participants to do is to basically change the variable here dot to use a Raja reducer object, and calculate the dot product of vectors A and B, and then just print out the value at the end. So let's take a few minutes. Feel free to go over the documentation. I'll answer some questions on the chat, and then we can go over the solution as a whole. Next. So just an overview of the solution, right? So the main the key uh line is right here, line 18. We simply replace the dot variable with a Raja reduced sum. The reduced sum is templated on an execution policy. Since we're running sequentially, we can just use a sequential execution policy, specify the type, which is a double. And here's an example of the dot product that I was leading towards. And finally, if you want to get the resulting value, there's a method called get in the reducers in Raja. Lastly, we of course yellow can allocate. So I'm going to pick it up, move on to exercise 6. So the objective of exercise 6 is to go over Umpire's different memory resources to allocate memory on the GPU. Okay, good question by Alfredo. So is it implicitly convertible to double? Um, it it can be, but the preferred way to do it is through the method called get. So lesson 6, Umpire creates these predefined allocators for each of the available resources. So you have a host and device available to you. You can allocate using the strings host device accordingly using the allocator. You also have support for things like unified memory and pinned when this is available. So in the example here, what we will be doing is simply using an allocator to allocate memory on that's specified on your unified memory. So this is memory that's going to be available both on the host and device. And then we'll do and we'll initialize the data. So we'll set it to ones, and then we'll calculate a reduction. And lastly, we'll print out the value. So let's take a couple minutes, and then feel free to explore this exercise. If you have any questions, please ask questions, and then we'll go over the solution. Thanks. Okay, so I'll quickly go over the solution, and then um, we'll move on to the next exercise. But the solution is simply in your allocator, specify that you want to allocate using unified memory, right, which is just done through UALL. And then we actually have the option of initializing the data using a sequential policy on the host or a device policy such as CUDA exec, or we of course template on the CUDA block size. And then when we do the dot product, as long as we're pairing the reduction in the for all execution policies correctly. For example, we're going to do for all on a GPU, we should use a GPU reduction policy. Then the calculation will work. We can do, we'll collect the dot product, and then we'll quickly print it out. Okay. So now I'll pass it all over to Christy, and she can take us to exercise 7.
Cool. Yes. Um, okay, let me share my screen here. Okay. So we can go to lesson 7. So this is where we're actually going to start seeing another memory resource. We have the device here, in addition to the host. But like I said, there's also pinned in all caps, and then which will give you pinned memory and unified memory, respectively. But for this particular example, we're just dealing with device memory. And then we're going to create a separate allocator on the CPU. So we're going to use the host memory resource for that. And then we're going to initialize some data on the CPU. But we want to do our computations on the GPU. So then we're going to use an umpire operator. So in this particular lesson, we're going to use the copy operator. So we're going to give it a destination pointer, which is going to be our GPU pointer, and then our source pointer, which is our host pointer, and then the size that we want to copy over. So yeah, the thing to note here is, usually you have source and then destination, but we kind of reverse it here. So the destination is the first argument. And yeah, so if you look in the actual code, you'll see that there is a couple of to-do statements. We're going to create our our host and device allocators, allocate some memory, and then use the copy operator to copy that over, so that when we do our very cool and exciting RAJA for all, it actually knows what these values are initialized with. So we can give you guys a few minutes to try and fill that in. And while you're doing that, I will leave it on the README where it kind of shows you the signature for this copy operator. So in the read the docs, we do have a word on our operations. That does not help. No. Okay. Yeah. So I thought I could look into it there, but yeah, I don't think so. Okay, so there is a question about the RAJA device. So while I answer that, I will take a look over here. So the RAJA device, little statement there, just means that where this code sits in GPU memory, it is accessible to the entire GPU, but the CPU has nothing to do with this, essentially. Yeah, Rich put in the chat, if you had instead put Raja_host, then this would be host accessible. Whoops. But then the GPU would have nothing to do with that code. And then, of course, you can also put Raja host device, and now it is accessible by the host and the device. Thank you, Rich. That was very helpful. Um, yeah. So if you want to use unified memory, you could do something just like this, but instead of device there, you just put and make sure that is in quotes. Um, so that is something you could totally do on this solution is just, edit that to instead, and that should work. Um, so if you got an error, it might have been in the way that this was, this was done. But okay, so for the solution to lesson 7, we just have these two copy operations where we are copying the data that is in the host version of A into the device version, and then we're copying the data that is in the host version of B into the device version of B, so that when we do this cool and awesome dot product, the GPU actually knows the initialized data in there. And then before we got a question about the dot get method, but this is, what that would look like. And now, we have our double dot, and then we can just do a normal C out down there. So this is like the recommended way to do that kind of thing. And yeah, so cool. I'm going to move on to the next lesson here, which is definitely my favorite lesson, where we start to talk about umpire pools. So in the case that for your program, you are doing a lot of allocations and deallocations of your memory, that can become expensive if you're doing like, large allocations, or you're doing this on different memory resources. It just kind of adds up. And so Umpire provides the memory pools, which is a more efficient way to make those large memory allocations. And especially if you're dealing with a HPC environment where you could be doing large GPU allocations, especially. So we have a couple of different what we call allocation strategies, but really this is essentially a memory pool. And so the one that we will be using in this lesson is quick pool. And it's well, like the name suggests, a faster, pool that we have. But we also have others such as dynamic pool list and fixed pool. There are certain advantages or disadvantages to certain other types of pools. For example, fixed pool, every single allocation you make is of a fixed size. So you just have to make sure that if you're going to use a certain kind of pool, it kind of matches your requirements. But quick pool is one that we recommend for a lot of different applications. It works very well. And you would be creating this memory pool similar to what we have here. So again, we're going to use the resource manager to make an allocator. In this case, it's going to be a quick pool allocator. And then there are two parameters that you would give it: the pool name and then this allocator. And the allocator is what you would have created before. Um, so, well, maybe there's an example of that, but when you used the memory resource, with host in all caps or device in all caps, that allocator that you created earlier, you will be essentially building a pool on top of it. Um, and um, and then yeah, and then we can go into some of these to the actual code, and I can show you what you'll be doing here. So in order to make these codes, compile, we had to, comment out some of this. um, but yeah, you need to uncomment out this compile thing, and so this will actually be compiled. We wanted all of this to compile even if it was missing a certain part of the code. But now that you will be putting in that part of the code, you want to uncomment this out. But yeah, so you just need to create your quick pool, and then it will be used here to do the device allocations. So the resource manager is a singleton, and it does keep track of where each pointer is. The operations are part of, well, they go through the resource manager so that you can, well, the resource manager will find out, what allocator those pointers are associated with and actually do that operation. So if you create allocators like this, they should be available. You know, that at the very least, but we've created instances that have GPUs on them, so there should be a GPU backend for this device allocator. But if not, we can look into why that would be. But that shouldn't be the case. Yeah, the resource manager is doing some bookkeeping on the pointers. You can turn that off. So there is a way. Well, I'm not seeing it here, but there's a way to turn off introspection. Disable introspection. Oh, duh, it's right there. So there's a way you can turn off introspection so that there is not as much bookkeeping going on in the background. Okay, so I am going to go into the solution here, and really the only thing that we did was create this quick pool allocator using the resource manager. So, it would get logged with the resource manager that you're creating this quick pool. You give it a name, and then you're building it on top of allocator, which will have device memory. And then, yeah. So with that, I will hand it over to Arturo, and I will try to continue figuring out some stuff from the chat. So
Thanks, Christy. So in lesson 9, we're going to go over some of the utilities that Raja provides. An example of this is the Raja view. So the Raja view, it was designed to simplify multi-dimensional indexing. So this is something that comes up in the way you want to access a matrix or a tensor, anything that's multi-dimensional. In many cases, we allocate data as a contiguous array. And what the view allows you to do is simply encapsulate that pointer and allow you to access the data through the parentheses operator in a multi-dimensional manner. So the Raja view has two template parameters. There's a type and layout. So type corresponds to the data type of the underlying data, and then the layout describes how the data is arranged. So the layout takes two template parameters. It takes the dimension of how you would like to access the data, and then the type. The type corresponds to the index that you're going to use to access the underlying data. So, for example, a 2D layout can be described in this manner. And since Raja follows C convention, the layout ordering is going to be that the rightmost index has the unit stride. So rightmost has the shortest stride, and then the leftmost has the longest stride. So when constructing a Raja view, the first argument is a data pointer, and then the remaining arguments are those required by the layout constructor. So in this example here, what we're doing is we're constructing a view, and you're passing the data pointer, and you're providing the extent of each dimension. So this is going to be an object of dimension n by n. So in the example here, the task is simply to create a view for pointers A, B, and C. And what this exercise does here is just does a matrix multiplication. So from the top, we're creating our pointers. We're going to ask for a allocator on the host, and we're going to be using a quick pool. So then we allocate our memory, and then we define our extents, our ranges for the matrices. And then the to-do here is basically an exercise for the participants to create the views that are going to encapsulate A, B, and C. Then you'll initializes the data, and then it performs the matrix multiplication. So let's take a few minutes there. Feel free to play around with the exercise, and then we'll answer any questions on the chat next. So to go over the solution is pretty straightforward. You can basically follow the example from the README. So you simply ask for 3 views, vTemplate on the data type, which here is a double. You specify the layout, template on the dimension, which is 2, and you create these 3 views, capital A, B, and C. and then lowercase a, b, and c correspond to the pointers, and the extent of the dimensions are as n by n. Okay. So with that, I actually want to pivot to multi-dimensional loops. So we'll go over lesson 10, and then we'll pivot into a set of slides for more intermediate features. But lesson 10 starts exploring how to write nested loops with the RAJA framework. So up to now, we've just been working with single level for all, which corresponds to single level loops. And for all methods, we don't recommend nesting them because it really limits the amount of parallelism you can expose. You can do it for the CPU applications, but it won't work on the GPU. So in order to address that, we developed the RAJA kernel API. So the idea for the RAJA kernel is that you use a policy to describe the loop levels in your algorithm. So the example here is we have a kernel that has 3 loop levels. We'll call it loop I, loop J, and loop K. And you can make a RAJA variant of this that utilizes the kernel policy framework, and you describe the loop levels in terms of statements. You have a statement for each loop level, and you can specify the loop ordering. So 0 corresponds to the innermost loop level all the way to 2, and then you can express how you want to dispatch each loop level. So in the example here, we have 3 perfectly nested sequential loops. And then lambda corresponds to the body of work within those loop levels. So this is how you express a set of perfectly nested loops within a kernel. And then within the actual kernel API, you template on the above policy, and you provide range segments for each of the loop levels, and you encapsulate them in a tuple. And then you have your companion lambda that encapsulates the work. So since we have 3 loop levels, the lambda is going to have 3 arguments. And this is supposed to be a mirror of basically how you express the code in C. So of course we have documentation in the RAJA docs. There's a background on the capabilities, the motivation. We have various examples here. So for our exercise, what we're simply going to ask is that you take this example and implement nested loops to initialize the data and perform matrix multiplication. So I'll just take a short few minutes here. I know we're kind of in the last part of the tutorial, and then I'll go over the example, and then we'll go over into more intermediate exercises. Okay, so just going over the solution in this example, we wanted to do matrix multiplication with kernel. So the first step is to create a kernel policy. We're going to do 2 levels of loops, and this is encapsulated in this policy here. We have the companion lambda that has the unit of work. So here we're just initializing the data, and then we have the actual kernel that does the matrix multiplication. So here's a good question by Alfredo, and I want to come back to your question when I get into the slides, if that's okay, because I want to dive into more CUDA and HIP policies, and then I want to And hopefully that kind of helps steer the conversation. So now we're going to jump into intermediate Raja and Umpire features. So we're going to be building off the kernel. We're going to be talking about nested loops. I can't see the chat, so hopefully, Christy, there's something I should address. Just unmute and let me know.
Okay, yeah, sounds good.
Thanks. So we've been talking about Raja for all. We've gone over reductions, umpire memory allocations, and now we're going to be going over more intermediate features. And we have a folder in the repository that begins with a fractal example. So everything we're going to be talking about builds on this fractal example. And just as a refresher, a fractal is a never-ending complex pattern that's typically created by repeating a simple loop. So the basic recipe is you have an equation. You take an initial value and you keep feeding the result the equation onto the equation a large number of times, and based on some convergence criteria, you can assign the result a given color. And the example that we have in the repository created this image here. So this is an example of what you can create. So a C-style implementation of the fractal generating code looks something like this. So in C, you would traverse the width of your image. So here we're always making perfectly square images, but you traverse the pixels in the column and row range, and you compute Cartesian coordinates. And here you have your equation that you're constantly feeding the solution to. So you have initial value, you feed it into the equation, keep feeding the result into that equation until some convergence criteria is met. And that can be a number of iterations, which is captured here by deck, or the result of the solution. And then you assign a color. So coming back to Raja kernel, a sequential implementation of this would look like this. So on the top part of the code, you have the execution policy. So basically, this describes how the loops are going to be executed. So kernel executes computational functions based on a sequence of statements. Here we have the for statement that emulates a for loop. And then Lambda, as I mentioned, invokes a body of work. So the actual kernel API takes a tuple of Raja range segments, which mirrors the bounds of the for loops. And then you have the loop body that looks exactly the same. So the CUDA variant of this simply requires modification on the kernel policy side. It does need the Raja device declaration. However, if you wanted this to be portable across host and device, you can simply use a Raja host and device macro, and then it's the code will execute on the host or the device. I saw some discussion on the chat earlier, so I'm very glad I can pull that back into the conversation here. So we have two loop levels, and what we're essentially doing is we're taking a global index of a compute grid. So here it's a 2D compute grid, and we're assigning each dimension to a loop level. So you can think of having a two-dimensional compute grid, and you're asking each thread in the X, Y dimension to perform the calculation of each of the loop levels. So what's templated here is the block dimension, and then the product of these values should be what's in threads. The key, something to note here is that this is the same code body as in the sequential version. In order to make this work for HIP, you simply have to replace CUDA with HIP. And then everything else is the same. So you can basically do string replacement, and it works on AMD devices. So an alternative to this is the RAJA Launch API. So the RAJA Launch API provides developers an execution space so they can express their code in terms of nested for loops. Um, so the RAJA Launch API looks like this. So the Launch API has a runtime backend selection, so you can choose to dispatch the code on the CPU or GPU. And then Launch is very explicit about device execution. So within the launch parameters, you specify the number of teams, which is analogous to CUDA blocks or HIP blocks. And then threads are the number, well, threads are the same as in CUDA and HIP, right? They're threads. So given a compute grid, threads are grouped in together into teams, and then you have you can coordinate, you can synchronize between threads in the team. And that's exactly what the launch context does. You can use this variable CTX within your kernel to synchronize threads within the team. And then here is your execution space. So here, this is where you can write your algorithm in terms of nested for loops. So as mentioned, RAJA Launch introduced runtime host device backend selection. So what this means is if you want to take advantage of this feature, your execution policies have to have both a host and device version. But of course, both are not required. If you just specify one, then you're committing to only to running on that given backend, and you have no runtime selection. So in this example here, we specify the launch policy, which corresponds to where the execution space is going to be launched. You can launch it on the CPU using sequential launch, or on NVIDIA using the CUDA launch policy. You can specify asynchronous or synchronous behavior of the kernel. And then each of the loop levels, you can specify to run sequentially or in or as before, assign each loop level to a thread in the compute grid, right? And the global threading policy, the threading policies are the same as what can be used in RAJA kernel. So in order to express your algorithm in terms of loops, we have the RAJA loop method, which is templated on the execution policy. And as before, we specify the iteration spaces using these range segments. Something to note here, though, is that once you're inside the execution space, your loops can capture by reference. And this is handy because if you have any values in between loops, and if you want to modify them within a loop, by capturing by reference allows you to modify that loop. Yeah, that variable.
So, Arturo, we do have a question. So if you want runtime selection, but you don't have nested loops, is launch API still a good path? Like, would you give it one team and many threads?
You could do that. Yes, that's an option. We also have a I'm forgetting the name. I think it's called dynamic for all method, and it's basically a very similar idea where if you have a single loop level, you can give it a list of policies, and then you can choose which policy you want to run at execute at runtime. It's under an experimental namespace, but the capability is there.
Um, and then there is another question that select CPU or GPU variable that you're showing on the slide right now. Is that a placeholder or a variable? And does it need to be consistent with compile tags specifying CUDA or,
Well, so that's a placeholder. I think the proper variable names are host or device, and it's under a RAJA namespace. Um, so if you compile, for the CPU, the device won't exist. So it's just you have to guard that. But if you're compiling for the GPU, the host and device uh, variables will always exist. And I hope that answers the question. Okay. So okay, cool. Um, so with just a quick comparison between kernel and launch. So what's different about these two APIs is that in kernel, kernel embeds the loop structure within the policy. Uh, so everything's templated. And in launch, the loop structure is within the execution space, right? So, and then there's advantages to both of them. So if you want to do loop interchange, you can do that uh, easily with kernel without changing your actual code. It's not as we can't really do that right now with launch. You would have to actually go into the source code and change the loop levels. But if you want to do something, if you want to have multiple sets of loops, maybe they're not perfectly nested. It can be easier to express that in launch versus kernel, where you may need multiple lambdas for different loop bodies. So, depending on your use case, it may be easier to express your code with one API than the other. Yeah, and then with that, I want to hand it back to you, Christy, and we can go over the fractal examples.
Yeah. Okay. So I want to be, cognizant of the time. We have 12 minutes. So, um, uh, I can share this. So in the Raja Suite tutorial, we have this intermediate tutorial. And so, I'm just gonna skip it because this is gonna be kind of fun. But essentially, we are creating a fractal, and it's going to have the Raja kernel backend. So we don't have too much time just because of the way things worked out today. But we can leave the instances running for a little bit longer if you're using the instance, and of course, LC is always available for the people who have access. But you would get rid of or uncomment out this comment here, and then toward the body of this kernel. Well, I guess the way that the fractal works is when you run it, you will give it a width, and so your fractal will be, let's just say 1024 by 1024 pixels, and then you give it this edge length, but it's really like a depth, or no, I think I've already said that the depth is 256. Yeah. So there we go. So you just have one parameter. You just give it a width when you run it. So that is something to just kind of be careful of. But of course, you will get an error message either way. But yeah. So then we are going to get our resource manager, like we always do. We're going to get our allocator. In this case, it should be some kind of GPU backend. So either device in all caps or UM in all caps will be good. And then you will need to create the quick pool that we've done before. And then we're going to be using that pool to allocate memory for this CNT array, which is actually going to hold our pixels. And And then the next thing um, that you guys would do is set up the Raja kernel policy. Um, and so um, I think, some of this has kind of been filled in for you. Um, but some things will still need a little bit for you to fill in. Um, and I don't know if we're going to, I think we're just going to go over the solution here.
Yeah, I
It's
think we're out
just,
of time. Actually,
yeah.
wondering if it might be good to leave a few minutes for questions. I also realized that I'm not sure if I answered Alfredo's question about um, in a multi-dimensional loop, what policies can really be nested. Um, how does that sound? Questions? Let me let me comment on this real quick.
Yeah.
Um, yeah. So if you have a multi-dimensional loop, what it really comes down to is what can you do on the device? Because on the CPU, right, you only have like sequential policies really. You may have like a SIMD policy which will hint vectorization. So I would say anything you would do in standard C, you should be able to do in Raja. For the device, what the way to think about this is have um, you have the dimensionality of the compute grid. Each of those levels can be mapped onto each of the loops. And then if you want something like hierarchical parallelism, which we unfortunately didn't get into this time, you can start mapping threads each loop level. Hopefully that helps. In the documentation, there's examples of which policies work with which API. And if there's any more questions, you can raise your hand or you can add it into the chat and we can simply discuss it here.
Yeah. The way that the webinars were created, um, you don't have the ability to unmute yourself, but if you raise your hand, I can find you on the participant list and unmute you from there. Um, Another thing that we could do, if there's no immediate questions. Oh, well, so Arturo, Alfredo has those.
I think I get your question. So we have policies in the X and Y dimension, for example. Are you asking can you collapse them into like one iteration space, like for example in CUDA? Yeah. There is I believe there is a policy for that. I think it's called like flatten, something flatten, like thread flatten. You do have that capability, and that has actually come up in applications where maybe you have two level loops in part of the kernel, but then you want to rearrange your threads, so it's just one giant it threaded dimension. So kernel fusion, so fusing loops, that can be done, I guess, in a couple of different ways. You can fuse loops in the sense that you can group them together and um, launch them all into a single kernel, and that's through the Roger workgroup mechanism. And you can also fuse loops using Raja kernel, and there's a um, fusion statement, I believe it's called. I think it's called fusion. And basically, it takes the two loops. So this is assuming you have your two loops encapsulated in lambdas. You can take those two lambdas and run them under the same loop. So that's one capability. And then there's like loop fission, which will break up your loops and execute them in terms of two different loops. And that's all available in kernel. And then there's a question here on explaining how unified memory works better. Um, Also, what memory allocation tool is usually used in production HPC? I'm not sure I understand the first part of the question.
Yeah, I think it kind of depends on your application. Um, Sometimes unified memory can be a performance gotcha, where um, it kind of uh, will make things go slower just because the memory will be accessible by both host and device, and that kind of requires some things to happen behind the scenes. Like if you're dealing with CUDA unified memory, is what I'm thinking specifically. But for the lab, we have Umpire that we use for um, our production codes. Our multiphysics codes. We'll use Umpire, and that's just because we need to target CUDA and HIP and possibly other backends, and we don't want to, um, have all the different code versions, available. We just want our memory allocation tool, Umpire, to just target that automatically depending on, what we have available on the system. But if you go to, another lab, um, they might have a different, um, memory allocation tool that they use. So it kind of depends, on what you're really trying to optimize for.
Oh,
Um,
I misunderstood the question. I think he's asking what is unified memory in general.
do you want to take a stab at that?
Sure. So unified memory, in a few words, is basically memory that's available on the CPU and GPU. Um, so basically, the software will manage moving the data back and forth for you. Yeah, that's basically it.
That is a good, concise way to describe it. Um, yeah, but since the software is managing, uh, you know, where the memory is accessible for you, it can be slower. Uh,
So Chai, question about Chai. So Chai will actually keep track of host and device memory for you. So in a given Chai array, uh, you allocate your memory, you just treat it as basically a vector, and you can do your operations with it. And when you're computing on the host, it will make sure the data is on the host. And then when you're computing on the device, it will do that transfer for you. It would be seamless. It acts as unified memory, basically. But it can be more performant than unified memory because it's doing the calls. It's actually moving the memory for you.
um, and there is also, MFEM can give you some cool memory management. I mean, I think MFEM uses Umpire, um, but there I mention MFEM because there is an upcoming tutorial on MFEM, um, and that is on the 22nd of August. Um, so, um, yeah, MFEM kind of provides some good uh, features along those lines. But with that, we have reached our, top of the hour. Um, And I can leave the instances running a little bit so you can kind of play around. We didn't get as far as we would have liked, but you can try playing around with some of the intermediate tutorial. I put the link in the chat there. Um, and it uses that fractal code for each of the lessons, and you are just giving it a cooler Raja kernel each time. And then in the last section of that intermediate tutorial, you can actually use Raja launch instead. And that is also, there's, a good example of how to use Raja launch in there and what it would look like. And of course, if you have questions, you can reach out to myself or Arturo. Um, if you go to the the Raja repo, there's links to like the mailing list and stuff, so that you can reach the Raja team even after this. Um, um, so a last question: does Umpire provide standard C++ memory resources and stateful memory allocators? So Umpire's allocators and memory resources would be uh, built on top of the standard, but I think we kind of um, you know we build on top of it to do what applications at the lab uh, need Umpire to be able to do. So like the memory resources, if you use the host, in all caps, memory resource behind the scenes that is using the standard C++ malloc, um, and then the device memory resource behind the scenes, it does use, a CUDA malloc or a HIP malloc. Um, I don't think you would want. No, I think the answer to can I use the STD vector on top of an umpire pool? I think that's no. And the reason behind that is that we want this code to be portable to the GPU. And a lot of like your um, uh, those types of data structures don't port well to the GPU. So we stick with, raw pointers, arrays, things that would be portable. And then Umpire has built on top of that to make it efficient and easier to use.